With the infinite limits that we've looked at in the last couple of videos, we've actually seen, okay, well, what happens if the y value approaches positive or negative infinity? And we ended up with vertical asymptotes. But we can also say, well, what happens if the x values approach positive or negative infinity? Because that's a possibility as well. So here we're going to establish some general rules for limits at infinity. We're going to look at some basic functions here to talk about, okay, well, what's happening as this function approaches positive infinity? What does that mean? What am I looking for? So we're going to start off with some simple functions. We're going to start off by looking at x squared here in parts A and B. And I think the easiest way to gain an understanding of limits is really just to lean on the picture. I would graph most of these. They're not too difficult to graph, and you can always use a graphing calculator if you want. So I know the graph of x squared, it's a parabola. It looks something like this. So in part A, we're saying, okay, as x approaches positive infinity, what's happening to my x value? So over here, as x approaches positive infinity. So really what that's saying is, if I move as far to the right as I possibly can, what's happening to my y values? So as I kind of trace this function and move as far to the right as I possibly can, what is my function doing? Well, the y value in this case, it's going up and up and up. I can just tell by that arrow pointing up right here. So if the y value is going up and up and up, it's increasing forever, we would say that this limit then, as x approaches positive infinity, must be positive infinity, because that's the y value. So the y value is getting larger and larger and larger and larger. Similarly for the opposite side over here, so for this side over here, let's do that in green. So here I'm talking about now the limit as x approaches negative infinity. I'm talking about this left-hand side. So here x equals negative infinity. I'm just going as far to the left as I possibly can. So here, as I trace my function upward to the left, and I kind of just say, okay, as I move as far to the left as possible, what is my y value doing here? Well, in this case, my y value is going up and up and up. It's increasing again. So the y value is approaching positive infinity here. So here, we would call this guy right here the right-hand end behavior, or the right end behavior. So as x approaches positive infinity, this limit is positive infinity. Here we've got the left-hand end behavior. So the limit as x approaches negative infinity is also positive infinity. X cubed we can think about very similarly, just the graph of the function is going to change. So here for y equals x cubed, we'll look at this guy over here. X cubed, hopefully we know that. If not, it would be a good one to have memorized. Looks something like this. So here y equals x cubed, just so that we don't mix them up. So again, I want to look at the right-hand end behavior. What is the y value doing as x approaches positive infinity? And here, whoops, this is a mistake. This should say as x approaches negative infinity, the left-hand end behavior here. So the right-hand end behavior, let's start over there. Let's do that in yellow. So okay, as I move as far to the right this way, right, as I move as far to the right as I possibly can, what is my function doing? So you can even start at the origin here. If I move as far to the right as I possibly can, my y value, again, arrow's pointing up, it's increasing, it's going up and up and up. So in this case, we would say that this y value is approaching positive infinity. So very similar to the last example we did. But in part D, we've got the limit as x approaches negative infinity here. Let's do that in a different color. Here we're saying, okay, as we move as far to the left as we possibly can, what is our function doing? Well, in this case, our arrow is pointing downward here, right? Our y value is decreasing. It's, I don't want to say smaller and smaller and smaller, but it's maybe we'll say it's getting bigger and bigger in the negative direction. It's getting larger and larger over there. So if it's decreasing, right, if my arrow is pointing downward, it's never going to stop going downward, then I would say that that y value is approaching, well, negative infinity there. So here, this one is a little bit different, and that's just because even functions work differently than odd functions. You can think about some of these algebraically by thinking about, okay, what happens if you take a very large negative number and square it, or take a very large positive number and square it. But I think the graphs are a lot easier to look at. E and F, here we've got 1 over x. That is the reciprocal function. So if you wanted to graph this, y equals 1 over x, it would look something like this. You've actually got a vertical asymptote at 0. It should see something like this. So this one is interesting. The end behavior is going to be a lot different this time around from the first 4 that we've looked at. Here, let's talk about this guy here in red. Now we're going to talk about the right-hand end behavior. So as x approaches positive infinity, so as I move as far to the right as I possibly can, what's happening to my y value? Well, in this case, my arrow's not pointing, say, or close to directly upward, right? My y value isn't increasing and increasing and increasing. Here, in this case, my y value is getting closer and closer to what looks like the x-axis. It's getting closer and closer to the x-axis. Well, the y value at the x-axis, right? This is really y equals 0. So as x approaches positive infinity, the y value is getting closer and closer and closer to 0. Similarly, on the left-hand side, if I say, okay, if I were to trace this function, if I move as far to the left as I possibly can, once again, it looks like it's getting closer and closer and closer to the x-axis. So in this case, we would say, well, if it's getting closer and closer and closer to the x-axis, that has a y value also of 0. So here, it doesn't really matter which direction I go. If I look at that end behavior, it's going to approach 0 in either case here. G and H, I've intentionally written a little bit differently, and that's just to kind of remind us of some exponent rules. We'll spend a lot more time talking about these later, but when we have a negative exponent, this really says, hey, what's the limit as x approaches infinity of 1 over x squared, and the limit as x approaches negative infinity of 1 over x squared here. So for that, again, we can graph this function fairly easily. Let's do that right here. 1 over x squared looks similar to 1 over x, but everything's positive this time. And again, we'll see a very similar story that we did last time, right? So if I move as far to the right, if I look at g first, if I look at the right-hand end behavior, my function is getting closer and closer and closer to the x-axis. It's getting closer and closer to a y value of 0 here. And if I were to approach negative infinity, if I move as far to the left as I possibly can, well, my y value again is getting closer and closer and closer to the x-axis. This has a y value of 0. So if we take all of these and sort of put them together, we end up with a series of statements about a function's end behavior here. So it says here, if p is a positive real number and k is some number other than 0, then the following holds. So if I look at these two, I think are kind of the most important. These are, I think, the most interesting. If you look at the limit as x approaches positive infinity or negative infinity, and you have a constant divided by a positive power of x here, so that x to the p has to be a positive power of x, then regardless of whether you approach positive or negative infinity, you're going to approach 0 for your y values. So both of those limits are 0. So this is going to be a really handy tool for us later on down the line. Limit as x approaches positive infinity, if you have, say, k times x to the p, so if you were to take that and bump it up to the numerator, here things get a little bit different. We can say, well, it's either positive infinity or negative infinity. We need more information, though. We need more information based on the value of p, and we also need to know what k is. Is k a positive number or a negative number? But if I know that k is, say, positive or negative, and I know if p is even or odd, then I can tell you what the end behavior of that function is. But for now, plus or minus infinity, that's about as good as we're going to get here. So one last theorem before we hop into a couple of examples. This is a really nice theorem. We could prove it, but it's a little bit long, and I don't want to take the time away from us here. This theorem says the limit of a polynomial function at infinity. This is really important. It only applies for limits at infinity. If your limit is approaching any finite value, this theorem doesn't apply here. So the limit of a polynomial function at infinity is the same as the limit of its leading term at infinity. So what this says is I can basically chop off everything that is not the leading term. I'm just going to look at the leading term, and then that determines what the rest of the function does. So let's look at a few examples here. I think I've got, let's look at these two right here. So I want to look at the limit as x approaches positive or negative infinity of, let's say, p of x here. So limit as x approaches, let's do positive infinity first. So here I'm just going to look at, well, what's the leading term? The leading term in this case is, well, 2x cubed. So this is really 2x to the third power. So this is really the only one that I need to worry about here. From here on out, you can sort of decide how you want to approach it. I might factor that 2 out, and I might say, well, that's 2 times the limit of x cubed. And then you say, okay, I know exactly what this does here. I know that that goes to positive infinity, so this is 2 times positive infinity. Here I have a positive number times another positive number means I'll get back a positive number here. So when we take a constant times infinity, again, really the only thing we're interested in, just like we were earlier, we're only interested in the sign. Do we get back a positive number or do we get back a negative number here? If I was to look at the limit, say, as x approaches negative infinity of 2x to the third power, here in this case, again, maybe we factor out that 2 and look at the limit as x approaches infinity of x to the third here. Oops, negative infinity. Lost my negative sign. Limit as x approaches negative infinity. Here again, so you can say, okay, well, the 2 just comes along, and then look at this piece right here and say, I know that this piece based on the graph of x cubed, and if you need to, draw that out for yourself. Here's the graph of x cubed, that left-hand end behavior that approaches negative infinity. So I have 2 times negative infinity. So what I have right here is a positive number times a negative number. Well, I'm going to get back a negative number. I'm going to get back negative infinity here. 2 times negative infinity, just get back negative infinity then. So again, when we're dealing with infinity, the sign is really, really what we care about. You can do kind of whatever you want as far as adding, subtracting, multiplying, or dividing by constants. The only exception is multiplying by 0, dividing by 0, things like that. Then it gets a little but for now, for the most part, say like adding a number, that's not going to do anything to infinity, or negative infinity for that matter. Let's look at one more here. Let's look at f of x, and I just made an executive decision that I want to change my mind on this problem. I'm going to change it up. Let's make this problem, how about negative 3x to the 6 plus 5x squared minus 8x cubed plus 1, something like this. I want to have an even power here just because we did an odd one last time. So here again, we're going to look at what is the leading term here. Well, the leading term is negative 3x to the 6th power, so that's really all I need to pay attention to. So I want to look at what is the limit as x approaches positive infinity, negative 3x to the 6th. We can say, okay, let's maybe factor out the negative 3, so we don't have to worry about that. X to the 6th here, this one is a little bit tricky because we didn't really talk about x to the 6th, but I can look at this and I can say, well, if you have an even power right here, x to the 6th, it's going to act exactly the same, or rather have the same end behavior as x squared. So this is going to look like negative 3 times, well, x squared, that approaches positive infinity on both sides. So I have negative 3 times positive infinity. So here I've got a negative number times a positive number gives me another negative number, so I end up with negative infinity for my right-hand end behavior. And then I'll look at the left-hand end behavior. Let me change up my color here. What is the limit as x approaches negative infinity of negative 3x to the 6th? Again, if you want to, you can factor that negative 3 out, and I think I'm just going to do that right here. Oops. Let's do that first. And then, okay, running out of room here. What does this piece right here do? Well, that piece acts a lot like x squared because it's just an even-powered polynomial here. So this is negative 3 times, again, positive infinity, since x squared approaches positive infinity on both sides. I've got a negative number times a positive number gives me, well, another negative number here. So here, it's really nice because I get to basically ignore everything else. So like negative 3x to the 6th, I got to ignore this 5x squared, negative 8x cubed plus 1. I really just got to say, you know what, let me look at this one single term. That is the term that really determines everything else that happens. One other thing that I will mention here, both of these examples, the leading term happened to be the first term. And one thing that I want to make sure that I clear up here, when we talk about the leading term of a polynomial, the leading term really is the term with the highest degree. Term with the highest degree. So in this case, since we're just dealing with powers of x, it's the highest power of x here. So if your polynomial was not written in standard form, if x to the 10th is your biggest power of x and that happens to come last, that means that is your leading term. The order that the terms are written in has absolutely nothing to do with leading term. We're always just looking at what is the highest power of x, and that will then determine the leading term of your polynomial.